Hello, good evening. Very welcome, very welcome, Sebastian Aristotelis, and welcome you all for this expert talk. The expert talk is called Desert, Arctic, and Ocean, Pioneering Space Architecture on Earth for Tomorrow's Exploration. I'm very happy to have Sebastian here. We just joked that he is by far the youngest space architect in our expert talk series by now. And I'm very curious and to hear his talk, because Saga Architects has really done a lot of pioneering work in the field of space architecture. And Sebastian Aristotelis, he's the lead architect and he's a co-founder of Saga Space Architects. They also specialize in 3D printing architecture and of course habitation for outer space. Though they have built projects in Asia, the Middle East, Latin America, Europe, and the Northern Greenland. You all probably know, because you are here to hear his talk, that Saga Space Architects recently sent its first payload to outer space, to the International Space Station. They have designed a lighting system, which is currently on use on the International Space Station by the European astronauts. And in his talk today, Sebastian Aristotelis will explore the journey of Saga Space Architects, and he will draw from his experiences with self-experimentation, because he was living underwater in extreme environments, but he will also share some projects from the deserts and Arctic regions, for examples from the Lunak expedition that was before the underwater analog project. And let's welcome Sebastian now for his talk. I'm very happy to have you here. Thank you for your time.
Hello, and thanks for the very kind introduction. So my name is Sebastian, and I'm sitting in a hotel room in London right now. And the internet has been a little bit tricky, but I think we have sorted it out. If there is any interruptions, it's only for 20 seconds, then the internet should be back again. Let me just share my screen. So I think, and please make some noise if you don't see my screen now. I think it was a great introduction, and my name is Sebastian. What you see in the background is one of our most famous projects, the Lunak Habitat, that we tested 1,000 kilometers north of the Arctic Circle in northern Greenland. We will get back to that. But down here's my contact information. You'll see it at the end of the presentation as well. If you have any questions beyond what we're going to discuss today, feel free to reach out and I'll do my best to answer. But I'm the co-founder and lead architect of Saga Space Architects. We are a little over 5 years old now. And as Sandra said, I'm 29 years old. We founded the company when I was 24. And knowing what I know today, I would still have founded the company, but it's been a painful journey, and it is, every project we do, we try to push the boundary of what's possible and what's not possible. So hopefully you'll see a little bit of that today. Just to summarize, we work with space architecture and Earth architecture, and we see that the technological kind of confidence that we get from space architecture is applicable in our Earth architecture, and the other way around, the sensibility and the materiality of the Earth architecture is something that we try to bring into space, especially the environment, nature, all of these kind of stimulations. Briefly, we are a Copenhagen-based studio. We are located in Denmark, Copenhagen, in an old industrial area, and we have renovated these old kind of manufacturing factory building into our workshop and our main office space. And what's interesting about our office is that we don't just design a lot of this stuff, we actually also build it ourselves. So we employ both programmers, engineers, architects, designers. We have one part-time psychologist, and I'm sure I'm forgetting something. And that is so that we can do all of these things completely vertically integrated in our facility at a short time, which means that we have a fast turnover of projects, and then we can keep the cost low. When you build stuff yourself, then people can tell you it's impossible. And I think that's also one of the attractive things about it. Last year, we had a big exhibition at the Danish Architecture Center. It's the most visited exhibition in the Architecture Center's history, I believe. Here you could experience a lot of our work, and primarily the Lunak Habitat that we brought all the way back from northern Greenland. Today, I'm briefly I will dig down into our method, how we go from concept to prototype, what we learned from it, and how we actually took some of those learnings, made it into a payload and sent it to space. So that will come in a bit. First, I'll just briefly mention why I think architects should work in outer space. In the very end, I'll tell you what's next. We have made the light in space. What's after that? So, as a brief introduction, I always like to show this image. It's Bruce McCandless in the 80s, and we have an image here of the longest untethered flight in human history. And we don't do that anymore in space. This is incredibly dangerous, and basically he's floating around outside the space station. With no tether, right? So with just his little jetpack, he can move around, but if that doesn't work, he's kind of lost by himself. And what's important to understand here, and everything in the space environment is almost trying to kill you. There's radiation, there's micrometeorites, there's huge temperature fluctuations, there's a vacuum, and then of course there's all the difficulties of the space suit, right? We've had several occasions where water have leaked and almost suffocated some of the astronauts, or other unimaginable, very difficult and dangerous things. And at the same time, he's completely alone, and all of his memories, all his friends and family is on the planet below him. So he's floating around in this dark, empty space. I'm sure he's having a good time, but it's also taxing after a while. And when he gets back, he gets into this, right? This is the space station. And even though I have a professional curiosity about the space station, it does not feel like a home. It feels more like a laboratory. And I think that is my entire critique of space architecture up until recently, right? And in the last 50 years, the entire space industry have focused on survival, with few exceptions, of course. I'll get to one in a moment. And that's also good. Survival is the first thing we need to solve. But we're at a point now where I think it's exciting for architects, because we need to thrive. We cannot just survive in space. And I think my favorite piece of architecture on the International Space Station is the Kuula. The legend goes that during many budget cuts during the development of the space station, the cupola got removed from the list of features. And somehow miraculously, it got added back to the program of the space station. And by some miracle, I'm sure it's not a miracle, it's a lot of hard work, but by some miracle, it made it into construction, and now it's on the space station, and it's almost impossible to imagine the space station without its most significant feature, the cupola. And if you ask any of the astronauts, and I've asked a handful myself, they will all tell you that the Kuula is their favorite place of the space station. If they have 5 minutes of free time, then they float here, they look at Earth, they take some photos, they think back to their family, they look at the mountain formations as they orbit Earth at 28,000 kilometers an hour. And then before this presentation today, I Googled what is the best day on Earth. And in this image, this is an image of Hawaii, and you can almost hear the rustling of the palm tree leaves. You can feel the sun on your face. You can hear the sound of the waves. I can almost taste the salty sea. And being in cold London right now, or coming from cold Copenhagen, this looks quite attractive to me. And it's actually an interesting image, and it's because it's taken from a quote by Jeff Bezos. I assume that you know who this is. It's the founder of Amazon and Blue Origin. And he argues that being in a space station, because it is completely mechanically controlled, you could make it like every day is like the best day on Hawaii. It can be 27 degrees, it can be sunny, it can be low humidity, it can be, and so on and so on and so on. The problem is, if you make a graph over the stimulation curve for a human being, it would be completely flat. If every day is like the same day, it doesn't matter if it's the perfect day on Hawaii, it would still be a flat stimulation curve. And what humans actually need is variation. And that kind of is one of the biggest things that we are working with. We are trying to figure out, how do we bring variation to the astronauts? And this also helps with the loss of time. So astronauts and people in quarantine and isolation in general, they experience they lose the sense of time. Did I call my mom yesterday, or was it 2 days ago, or did I talk with my crewmate 5 days ago? And all of these things, they kind of flow together because the food is the same, the conversations are the same, the people are the same, the climate is the same, everything is the same. So we need to bring in stimulation. Okay, but with a little kind of introduction to why I think space architecture is important, I'll briefly go through some of our projects. So the Lunak Habitat, which we won an Index Award for in 2021, is an unfolding origami habitat made out of carbon fiber and aluminum. And it expands 750%. And the reason why it expands is because we know that the limitation of space architecture is volume. And you need, and weight, of course. You need to send something in a rocket to a different planet. It's limited by the size of the rocket. So we thought it would be a great idea to figure out how to make a closed volume rigid panel expanding structure. This is what it looks like, and you can see here one of the benefits of the hard rigid shell, which is you can mount solar panels directly on the facade of the structure. There's no, from the outside, as an architect, it's important to say that there are no outside considerations for aesthetics. It's black because the carbon fiber is black. It's raw aluminum because you can leave it untreated. And we picked aluminum because it's soft, so we can machine it. It's softer than steel, but at the same time, in the cold conditions, it actually has great performance. And it's lightweight. So there's considerations for all of the decisions, but they are not aesthetical. The Danish national TV made a documentary series about me and my co-founder's expedition. Me and Carl Johan, we spent 100 days in the Arctic, lived inside of the habitat for 2 months, for 60 days on 4.5 square meters. And then why did we pick Northern Greenland? We picked it because of its similar lighting environment to the moon, right? We wanted to make, before making the project, we kind of sat down with a blank piece of paper and we said, how do we make the most realistic moon analog that has ever been conducted, right? Okay, the lighting conditions, that's something we need to emulate. The big, vast landscapes, like there's not a lot of plants, there's not a lot of animals, there's a lack of stimulation, just like the moon. There's extreme temperatures. And why are extreme temperatures important? Well, I think it's important that it's difficult to go outside of the habitat, because in space it's difficult to go outside of the habitat. It needs to be isolated. If you as a human being know that help is just around the corner, then it's not realistic stress. It's not a realistic amount of stress, because stress is a very biological response. That means that stress is not something that you just simulate. Either you are stressed or you are not. And if we want to test how well the architecture performs in coping and making countermeasures for the stress for the astronauts inside it, then we need to have the stress as well. So all of these things all together make for a very realistic analog. I'm just going to check in and see that I haven't lost the connection and that you're all with me, and it looks like we're still here. All right. Whenever we went outside on this expedition, we would wear our spacesuit. We had designed and 3D printed a carbon fiber PETG protective helmet, and we did several expeditions outside, but always wearing our suit. And to give you a little bit of context, this is what a storm at 24 meters per second looks like. This is what a hurricane at 32 meters per second looks like. And here in a little bit, you'll see the roof of this building in Florida getting torn off. There we go. And the fastest wind speed recorded in human history is 93 meters per second. And it's recorded very close to the area where we were. And that's because you have the ice cap in the middle of Greenland, and you have some very big winds coming in from that. So that's the context that we had to make the habitat survive. Of course, we have very cold temperatures. We have minus 30 degrees Celsius with a wind chill of minus 41 degrees. I was giving this presentation in Greenland last summer, and of course, for the people in Greenland, this is just an ordinary autumn day. So they were not very impressed. But for me, that was very cold. And for most people, minus 30 degrees Celsius is extremely cold. And I can tell you for electronics, it's very cold. Stuff starts to break and not function, and materials and insulation gets rigid, and your fingers get numb, and you try to put on bolts, and it's a big mess. All right. And inside the habitat, so here's a cross section, and if we do a plan section at the ground floor and at the second floor, it looks something like this. And the first area is a toilet. That's our airlock as well, so it has a double purpose. Then we have the living quarters, and in the living quarters, that's where we spend 95% of our time. Then we have the sleeping pod, and I'm 183 centimeters tall, so I fit quite nicely right here. But you can notice that Carl in the blue sleeping cabin, he is eating 20 centimeters of my foot end, because he's 2 meters and 5 centimeters tall. So he's very, very big. So we kind of said jokingly that if Carl can fit inside the habitat, then anyone can fit inside the habitat. This is what it looks like. And of course, it's funny, whenever I see these images from the mission, because, we were in complete isolation. It was just me and Carl. So, one of us had to climb up and place the camera and put a timer and go down and pretend that we are working. But so all the images taken on the expedition is of course something we took ourselves. And this is what it looks like. And we could talk for a long time about this project alone. I'm going to keep it brief, but we have VHF radios, we have a satellite phone, we do not have internet, we do have video recording equipment, and some other safety measures. But this is what the crew quarters or the sleeping cabin looks like. That's the most private area of the habitat. And we made a decision that I would never ever enter Carl's sleeping quarter, and he would never enter mine. And in that way, we have a kind of a fake sense of what should we call it, privacy. Because of course, in a habitat like this, that's so tiny, there's no privacy. So it's all an illusion, but you want to keep an illusion of privacy. Here you can see a closer look up at the spacesuit. It's an Arctic expedition suit that we modified. It has electric heating, batteries in the pocket. We have 2 or 3 layers of gloves on, protective helmet with communication, light, camera recording. And we would wear this when we were working outside, setting up the habitat in very, very cold weather. One of the interesting things that came out of this, and pay close attention to this, we'll bring it up a little bit later as well, but that's our circadian lighting system. So we developed this lighting system that mimics sunlight. And that's because for the last 30 days of the mission, we didn't have sunlight at all. It was complete darkness outside. So by having this synchronized light inside the habitat, it was in the sleeping cabin, it was in the crew quarters, it was in the airlock, and it was all running synchronized. It was possible for us to have the sensation of time, right? So in the morning, we would wake up with a sunrise, daylight, different types of daylight, then a sunset, twilight, and darkness. And all of these things made us differentiate time, and it also helped us sleep better. This is just an image of the most beautiful sunset during the entire expedition that it was so nice and red, I had to take a photo. And this is the last image taken on the expedition. You can see the moon here, full moon during peak winter. Mars right here shining bright red. The habitat in the middle. I think it kind of captures everything. So how did we do it? I wish we had 5 hours to talk about this, but I'll try and keep it brief. We start with sketches. We always start with 100 sketches. Doesn't matter what project we're doing. Come into our studio and you'll see that we have 100 sketches for each project. Then we start 3D modeling. We start becoming more mature. We see that the Mark I, which is this big, couldn't fit inside the shipping container that we had to ship it with. That's not good. Then we made the Mark 1.1. It's smaller, fits inside the shipping container. Carl can't stand up inside it because he's too tall. We have to make it a little bit taller. We make it taller and skinnier. And now it fits inside a shipping container and Carl can stand inside the habitat. Everyone's happy. We start simulating the folding origami pattern. A long process. In the next couple of slides, you'll see 3 slides, but it's really a development over 9 months, right? So, we 3D print a small sample, it works. We figure out how to simulate a cylinder. We use Grasshopper to do that. We continuously build 3D printed models that continues. We built a full-size mock-up out of cheap materials, cut on a CNC machine, just to test out the ergonomics inside the habitat, made out of timber and MDF and 3D printed joints. During the development, we were sleeping in our workshop in this habitat, both to test it, but also so we didn't have to spend any time on commuting. Because at this point we were working, this is the beginning of the company, we were working 7 days a week. Every single hour of the day we spent on this project. And the entire team did, even our girlfriends, everyone was just invested in this project to make it work. Finally, we get to a shape that folds beautifully. It's closed at the top. We can mirror that and close it at the bottom. We bring it to a full-scale mock-up, still out of cheap materials, that folds, and then we start manufacturing of the final thing. And just to give you an overview of what we had to kind of go through this project, we were both the developer, we were the designer, we did all the engineering, we did all the construction, we did all the logistics and mission planning and finding insurance and all of that. We did the fundraising, transport, the assembly on site, right? We did all the research, 9 international research projects. We had to conduct all the science when we were there. We filmed 2 documentaries, also ourselves while we were there. And it was too much, right? You should never do this much, but there was no one else to do it, so we had to do it. And people always ask me, so how do you fund these projects? And funding is that's one of the money is amazing. It's the best resource to build the stuff of your dreams, right? And that's something I can feel for myself. It's like if you have enough funding, you can do whatever you want, right? But what we did was, because we didn't have funding, we sat down during a weekend, made some drawings, rendered it out, made this beautiful landscape, two astronauts walking towards this in an ice landscape. I think it's actually the astronauts from Interstellar I cut out and photoshopped in. And then we just made something that looked like a space habitat. We had some ideas about it. Maybe it could look something like this, but we needed something that looked real, that we could bring to companies and to grants and funding opportunities around Denmark and say, hey, this is a project that we are doing. We are not crazy. Look at it. It looks real. Do you want to support us? Do you want to sponsor anything from carbon fiber to aluminum to batteries to whatever? And we used this drawing. And then for the next year, we spent actually designing, testing, and building the habitat. And once it was finished, we updated the drawing, right? And we went to our partners. We said, okay, we changed the design a little bit. Do you still want to be a part of it? Of course, they all wanted to participate. So, I think the lesson here is for us, it was very important to just begin and to do something, because if you just sit and think about it, you can do that for a very long time. So we ended up having a lot of partners, international and local, everything from Garmin to Lenovo to the Danish National Technical University, and it's companies that we work with to this day, right? So, huge LEDs are manufacturing the LEDs for us that is now in space, and all of these things started. I'm still using Bosch tools down in the workshop building this stuff. Everything started with this project. We also did a little fundraising on Kickstarter. That's an important part of the narrative, and that made the last stuff possible. That kind of brings me to manufacturing. I'll go through this very briefly because we have a lot of stuff we need to go through. But we did a lot of CNC machining, learned how to machine aluminum, assembled all the parts, made threads. Didn't know how to do that before the project. Learned it during the project, welding as well. Here's one of our team members, and this is actually my girlfriend putting on insulation on the interior. This is our metal workshop, and that's the team working. We were working day and night, especially up until the end, sleeping in the office and the workshop, and everyone was coming. Parents came with food and beverages so we could work and didn't have to think about cooking. And then at that point, now we have a bit more heavier equipment and machines. At that point, we did not, right? So everything is raised by people power and moved around, and that was very heavy. And here in the bottom, you see our protected battery bank of about 140 kilos of lithium batteries. This is 16 hours before the container had to ship. And we finally fit the habitat inside the container. After that, it's just me and Carl in Greenland. And when we started, it was in the summer or in the early fall, and in the end, we were there in the winter. We had to secure the habitat to the ground using these earth anchors that was 1.5 meters, hammered them by a big mallet, and just hammered them down into the permafrost. And that was a tough task. And that took us 10 days. 2 people hammering 10 hours a day. I don't ever want to do it again. At the end of the day, my hands were buzzing like I imagine the coal workers did 100 years ago. It was the most painful thing in -degrees. Me and Karl-Johan didn't speak for 3 days, I think, because there was nothing to say, right? They are finally hammered in, big cables up to secure it to the ground. And then finally, that's the habitat. We learned a lot, right? And we took those learnings and then we put it into the next habitat, which is the Rosenberg Space Habitat. There was a client involved this time, and together with the client, it was actually a co-collaboration. The client added a lot of value to the project as well. It's an educational institute, and together with the students, they came up with ideas, and we tried to implement them as much as possible in the design. If I'm running out of time at any point, just let me know. I have enough time, so I will just go through everything. But if we are running out of time for the event, just let me know. This is the Rosenberg habitat. It's a static habitat, which means it doesn't expand. It's the tallest 3D printed polymer structure in the world. We built this 2 years ago. It's still the tallest structure at 7 meters. This time it was designed for the new SpaceX super big rocket, and it's so big that you can actually fit 6 of these habitats inside. So when we started the project, we had to figure out, in such a big rocket, what is the optimal shape to put inside the circumference. We started with a cylinder, a circle, and that only gives you 67% utilization of the cross section. We tried a triangle that gave us 83, and then we tried the curved triangle, and that's actually the optimal shape to fit inside of a slice of pie, right? So that's 86% optimization, so very little wasted space. And then we tried to figure out the exact curvature of the walls and how pointy the corners could be. And of course, because it's a pressurized volume on the moon, there's no atmosphere. The sharper the corner, the thicker the walls needs to be. So this is a parametric simulation of that wall thickness. And we tried to find, you want straight walls because that's easy to live inside. If you live inside a sphere, that's difficult. We cannot put any flat things up against the wall. So we want to try and have flat walls, sharp corners, but we don't want it to be heavy. And in the end, and this is another simulation, you can see here the wall thickness increasing. And of course, a round shape like a balloon is the most efficient, but that's very difficult to live inside. So we want to balance livability and structure. Then we used an algorithm called topology optimization. This is not something we invented. We just used somebody else's algorithm to optimize our shape. And what we did was we ran a topology optimization script. And of course, it still took us 3 months to make this work on our structure. And then we simulated the loads of that would act on the habitat, the pressure inside, loads during the launch, landing, raising the habitat. And what it leaves once the algorithm is finished is a nice web of material, almost like nature. It removes material where it's not necessary, and it adds material where it's the most necessary to keep the structural integrity of the shape. And then we figured out we have this crazy shape. How are we going to build it? We ended up 3D printing it, and that was not easy as well. I had to basically look at all the 3D printing companies around the world. I cold called all of them and said, "Hey, we have this crazy project. Do you want to 3D print it? We almost have no budget for it, right?" And finally, a company actually, so at that point there were only 2 big companies that could kind of do this, and one of them agreed. And it was a wonderful partnership with Ingersoll in Milan. They also have a US-based entity, but because we're in Europe, we flew to Milan, and there we printed these 7-meter long panels out of a composite that we made ourselves. And it took 12 hours to print one section. There's 6 sections to the shell, and it's actually very lightweight. It's only 5 millimeters thick. The structure is inspired by what we learned in Greenland, and the organization inside is almost the same. Besides, we added another floor. You have the airlock, you have the workshop, trying to use natural materials like cork, that are still space grade, but has a natural feeling to it. This is the living quarters, and then the sleeping pods. All right. I can see the time is ticking, so I'm just gonna speed up a little bit. But that kind of brings me to the circadian lighting. So of course, in this habitat, we also included circadian lighting. So you have a sunrise and daylight and sunset and twilight and all these things. And then the Danish government called us and they said, okay, Andreas Mogensen, the Danish astronaut, is flying to the International Space Station in about a year. Do you want to participate? Do you want to send an experiment with the Danish astronaut? We are inviting Danish companies to pitch. And then that's not an opportunity you say no to. So I just said yes, went back to my team, and I said, okay, we have this opportunity. What should we send? Or what should we pitch to the Danish government? And we pitched the idea of the circadian lighting system that we tested in Greenland and now in the Rosenberg habitat. And of course, they absolutely loved it. Then we had half a year to develop the hardware and send it to NASA. And that was, of course, the biggest challenge that we had ever faced, right? This is the first piece of space grade certified payload that we have ever built. This is the final product. And what it basically does is we know that 75% of astronauts, they use sleep medication. That's incredibly bad. And sleep is one of the most beneficial biomechanisms that we can do to our own well-being and health. So we want to make astronauts sleep better. And you know, it's interesting that the solution is not in space, it's actually down on our planet. And it's just mimicking the sunlight that we take for granted. So what we did was we just took the spectrum of the refracted light through our atmosphere through 24 hours and put it into a light. And of course, that's easier said than done. It was incredibly painful. It's the reality of making payloads for space is that, I learned that it's 5 to 10% design and creativity. And then it's 90 to 95%, certification, documentation, safety requirements, communication back and forth. And it's still a wonderful experience, but it's like with any great thing, it's actually a painful process. But we made it. There's a lot of different components that went into it. There's all kinds of different things and details I could tell you about this light and why I think it's one of the most impressive lights that's ever flown in space, if not the most impressive light. But and let me just go here to the functions. The key functions that the light has is that there are 3 faces to the astronaut. One is facing directly to the astronaut, one is facing down, and one is facing away from the astronaut. In the morning, there's a sunrise filling the ambience of the sleeping cabin. Then there's direct sunlight, or a direct light down that's like a task lighting, and then you have the blue light facing the astronaut. The blue light has a specific spectrum of light that we know are healthy for humans. And we know that specific wavelength of light activates a specific receptor in our eye that we don't use for seeing, but that controls our circadian rhythm. And a combination of these 3 phases turn on and off throughout 24 hours. And here's a preview of that. It looks something like that. And that shift in light is the optimal, at least what we think is the optimal light, artificial light that you can have in 24 hours. And this is what it looks like practically. So this is morning, this is daylight, this is sunset, and then darkness. And sunrise, kickstart with the blue light, daylight, and sunset. And then we have different days. So, we also have variation between the days. So a Monday is different than a Tuesday, and a Tuesday is different than a Wednesday, and so on. Yeah. Right now, it's on board the International Space Station with the Danish astronaut. We don't know what the science is yet. I hope it's good. I hope he comes back to Denmark and lands on the ground and says it's the best thing that ever happened to the space station. I think that's probably a little too optimistic, but we are doing the science together with MIT, Lonnie Peterson, and Surrey University with Konstantin Stedev, and so far so good. The last thing I want to show you, when we did the Lunak Habitat, we looked, the Arctic is the best place for a lunar analog. But what is the best place on Earth for any space environment? And the funny thing is, Earth is 71% water. We call it Earth, but it's only 29% Earth and it's 71% water. So we should really call Earth water. So we call it the blue marble or the blue planet, but we still call it Earth, which is kind of a strange thing. But in the water environment, I think we can find the most realistic place for any space mission. So realizing that, a couple of years ago, we started the initial planning of a habitat underwater set for 2026. It will be a large habitat for 3 to 4 people. And to do that, we decided to make a pilot habitat in 2023. That pilot habitat we completed in September. Successfully, I lived inside the habitat for 48 hours at 7 meters depth. This is a rendering of what it looks like. Just to give you the full idea, it's a tiny habitat just to learn. The final purpose will be astronaut training, underwater science, and technology readiness level growth platform, right? So that's down the road, but right now we're still designing and building. So why underwater? Well, similar to, I gave you a list of 5 items for the Arctic environment, why it's a great analog for Moon. The underwater environment has been used by NASA since the late 50s to train for missions, and that's because there's no air to breathe. It's cold and uncomfortable. There's a pressure difference. It's isolated and confined. There's poor visibility. It's good for simulating microgravity. There's no sunlight. At least there's very limited sunlight, and then you have restricted mobility. And all of these things sound very similar, right? They sound exactly like what you would expect from the space environment. So this is a photo of it shortly before we tested it underwater. This is me underwater for the first time we tested the habitat, and then a week after I lived inside of it. We have a small documentary online that you can watch now. It's called Diving Deep to Explore the Stars.
After 48 hours,
I hope that the reception is okay now and you can see a little bit.
Bubbles have saturated my tissue in my entire body.
Yeah.
So I cannot just go up to the surface if I have to. I need to do an evacuation. And all of these challenges together makes the underwater environment the best place to test space architecture.
I just have to go here. I think it's a pretty good documentary. I would recommend to see it. But we completed it in the 23 to 24th of September 2023. Again, build everything ourselves. We also built the communications system and hardware. And then, of course, we're working towards the full underwater habitat in 2026. This is just a rendering we made. It's probably going to change, not going to look like this, but just to give an idea. So that's it. That's me. I think I went a little over time, but I have time for some questions.
Thank you very much, Sebastian. Impressive package of interesting projects.
Thank you. And we also did work in the desert. Preparing for this presentation, I realized we were running out of time, but we did work in the desert, and there's great things to learn from the desert as well, but we'll have to take that another time.
I take this as a yes to lecture in our MBA.
I would love to.
Great. Okay, before we introduce the students to the MBA programs, we have a lot of questions for you.
Yeah.
And I would like to ask the people to turn on their cameras and ask the question to you in person. So the
Yes.
first question is by, I'm sure I pronounce it very wrong, Yashi or Yatski Demirbas Pech. Please help me with your name.
Yeah, that's Yazgi.
Yatski?
Yeah, thank you.
Okay, right. Please ask your question.
Yeah, actually, I've seen your expo in Denmark last year, and I was
Amazing.
very impressed. But the question I have asked myself, and I couldn't find the answer in the expo, was the detail in the foldings of the habitat. Like I imagined that when it folds, all those layers coming on top of each other gets a bit like maybe yeah, more vulnerable to the crackings. Or I've seen that there were some materials that were really elastic or flexible, but still it was a bit yeah, it was the question I was asking myself, if were there any temperature fluctuations or any kind of difficulties you had regarding that subject.
So it's a good question. So the rigid panels were carbon fiber. In between the rigid panels, there was a composite nylon rubber material, like a reinforced rubber material, and that performed. We specifically chose that material for the Arctic environment. For space, you would choose something else. For the Arctic environment, this material is used for conveyor belts in mines in the Arctic, or in, so, and or it's used also for snowmobile tracks. So it's great for the Arctic environment. But that being said, of course, the insulation behaves a little bit strangely. It's not an issue really. We were warm and comfortable inside, but at very cold temperatures, some foam materials, they become brittle. So as long as you don't heavily mechanically, hit them or manipulate them, there's, the insulation properties is the same. So, but the insulation became a little bit brittle. As soon as you heat it up, it's soft again. So we didn't experience any challenges there. Let me see. With taking what we made as a prototype and making it completely airtight, I would say it's quite airtight. But if you had to make it completely airtight, that would be a challenge, right? How do you manufacture like a complete web of this flexible seam and make it airtight? That would take a long time to figure out.
Yeah, thank you very much.
Thank you very much. Bill, you are the next. Bill O'Hara, would you like to ask a question yourself, or shall I ask it? All right, hello. We cannot hear you. You are unmuted. Thank you.
Thank you. Yeah, I had asked about consumables during your mission in the Arctic. How did you handle water and food?
So we actually we had our idea was to follow what we would expect from a moon mission, where the astronauts would harvest the water ice for drinking water and for cooking, and that's the same that we did. So we had powdered food, dehydrated food, about 200 kilos of dehydrated food, and then every day we went outside and chopped some ice and brought it inside the habitat and melted it, and that's actually what we used for drinking and for cooking. It was not a great culinary experience, and I think depending on who the crew are, they might have other needs. I think our taste is quite simple in terms of food. I thought it was fine, but I can see how other people would be challenged.
Right. Okay. Thank you.
Thanks a lot. Leila.
Hello.
Hey.
I just had a quick question, is how many people ended up building Lunak? Because I think you had the original team and then you had all of your support team around you.
Yeah.
And I was wondering how many you had, and also, cheeky last question, how many people are working with you right now?
So we are, yeah, so before Lunak, we were basically 3 people. And during Lunak, we grew to around 18 people, I think. And now we employ, depending on the project, but we employ about 14 people. Yeah, and that's a mixture of different disciplines. Yeah.
Nice, well done.
Thank you. Mayur. Okay, Mayur asked the question, how do you foresee building information modeling, BIM, contributing to the efficiency, risk mitigation, and overall optimization of crewed spacecraft projects?
Yeah, that's a good question. So at the speed that we are drawing and 3D modeling, BIM is just too slow. And that, we keep going back, and our geometry is so strange, and we keep going back and forth from the workshop and then drawing and then testing it out and drawing. But as our structures mature, as they take longer time, as the requirements increase, then there's a time to transition into BIM. And I see a future. We have a partnership together with Autodesk, both for Revit and for Fusion 360, and I see a future where our entire habitat is a complete BIM model, and we actually, this is something we tested in Greenland as well, and we have a complete digital twin of the habitat, and we actually use that digital twin to do predictive maintenance on the habitat. This is like, and we had an algorithm running in Greenland. How successful it was, I'm not sure, but we had a 3D printer so we could fix things during the mission. But the idea was there, and I think it's just about time until we perfect that technique. Yeah.
Thank you very much. The next question I have answered for you, it was a link. And we have now Andela Kovacevic.
Hi, so my question was, did you develop any new materials for the habitats, or it's something that is already in commercial use?
Let me think. So Lunak was, all of it was, it's commercial use. Yeah, it was not for consumers, but some of it was for companies, right? So I think the most exotic thing was the carbon fiber sandwich panels that the rigid structure is made out of. Everything else is kind of off-the-shelf materials and off-the-shelf components for the Lunar habitat. For the Rosenberg habitat, we did make a proprietary blend of a polymer and some fibers, actually silica particles, and a UV stabilizer, and a little bit of white pigment that was specifically designed for the purpose of that 3D printed habitat. But we did that together with a chemical company that knew specifically and much more about it than I do. But I think, I have a list of things I want to personally be better at, and material science is one of them. And I think, material science is so complicated. It is so complicated. And I value the good material scientists and material engineers that are out there. And I think there's definitely a lot of value in that. Also, as especially when we talk about our Earth architecture, when we have to do more climate-friendly buildings, and there's also a lot of value to be gained there.
Thank you.
Maybe I would also like to add something, because when you say you use off-the-shelf materials, still means that for the specific purposes you were inventing new compositions.
Yes, absolutely.
New
But
geometries and new
yeah,
ways of connections. So that is a highly intelligent, smart way of fitting things together that are there. So that has in itself a high value.
I'm very happy you say that because I think we really pride ourselves on taking off-the-shelf components and try to make them space grade or work for the extreme environments. And we do that with everything. Also, our land and space. You of course have to make some considerations in terms of off-gassing, safety requirements, and all of that. But there is a lot of standard components. We also certified. We have that's a rabbit hole of stuff I don't want to talk about. But I completely agree. Thank you for saying that. Yeah.
Okay, we have a last question because then we have to move on to the introduction session. It's from Francesca, and she asked me to read it out loud. The question is, did you perform any experiments while in Iceland? I didn't get for how long you were there. And finally, what are the main findings and the next steps? Thank you.
Yeah, so great question. It was in Greenland, by the way, in northern Greenland, close to Iceland, but it was in Greenland. And we were there for 100 days in total, but it took us around 30 days to set up the habitat and the camp because we were only 2 people. And we were inside the habitat for about 2 months. So altogether 100 days, 2 months, and 1 month. So that was the first question. The second question was, what was the second question? Sorry. The main findings.
Main findings and the next step.
So the main findings, I have to say. Wait, so the main so there was a lot of psychological findings that we're using in our work. The main psychological finding, maybe it's more anthropology in a way, or social studies, but the human ability to adapt. I don't have a military background. I've never been to, I don't have any official training, and neither does Carl. And somehow we managed to live comfortably in this extreme environment. And I remember specifically after 4 or 5 days, the habitat felt like your home, right? And I think that's incredible power of the human mind, that we can adapt to extreme situations very fast. And I think that's a survival instinct. So that, I think, and that's one of the things I remember very clearly. From a space architecture point of view, of course, the biggest finding was the circadian lighting system. Before the mission, I had insomnia. After the mission, I still sleep like a baby. And I use what I learned living with the circadian lighting system. And that's why we are pursuing it so heavily and sending it to space, is because how well it worked. That would be the biggest one. And then next, of course, we are working underwater. That's kind of occupying everything I'm doing right now.
Wonderful, Sebastian. I thank you very much for your expert talk, and I'm looking forward to have you at the TU with our MBA students, where I would be interesting to hear more about your challenges, hurdles that you have overcome, and how you did it. I think you have a wonderful example of a young, innovative company, interdisciplinary company that's needed in space architecture. And as you said, if you have to take the opportunities that you have, and if there are none, you have to create them.
Yeah, I think that's wise words. I would love to participate. So let's just write after this, and then we'll figure something out. Thank you so much for today.
Thanks a lot, Sebastian.